Okay. And I guess it's a general phenomenon in mathematics, particularly, for example, in harmonic analysis, that there are aspects of problems that are very easily handled on the kind of time domain, and there are aspects of problems that are very easily handled on the frequency domain. But generally, something that's easily seen, for example, in the frequency domain, is rather obscure in the time domain. So basically, what I'm trying to say is that the Fourier transform is extremely useful. And just some examples that I find really inspiring. I'm not sure if you know this story of Fraunhofer lines, which is, if you look at the sun, if you just take sunlight and shine it through a prism, then what Fraunhofer first observed is that you almost get a rainbow, but that there's certain black lines in this rainbow. And what Fraunhofer, I think, conjectured, and then others about 30 or 40 years later proved, is that these missing lines are exactly the absorption spectra of certain elements in the sun. So to us, we kind of live more naturally over this side. We just think that sunlight is sunlight. But once you take its Fourier transform, you notice that there's certain missing spectra, and this tells us about the composition of the sun. So this is the story of Fraunhofer. Lines. And also this tells us about the composition of stars and pulsars and things like this. Another example is the Riemann zeta function. Okay, so there's aspects of number theory that are easily seen over this side, but then there's aspects of number theory, for example, the prime number theorem, that are much more easily seen on the frequency side. And you can think about the kind of, for example, the zeros of the zeta function as being the kind of Fourier transform of the prime numbers. And I recently went to a talk by an Australian statistician who is one of the leaders in a project to compose a very reliable map of CO2 distribution in the atmosphere all around the world, so that you can locate sources and sinks of CO2. And the main tool that they use is a NASA satellite that's orbiting the Earth, and basically just looking at the light coming from the Earth's surface. And the remarkable thing is that by doing a spectral decomposition on that light, they can tell differences of a few parts per million of CO2, which I find totally amazing. Okay, so this is just this to emphasize this fact that the Fourier transform is extremely useful. So it's often useful to think about, one can think about of derived categories as kind of categorical function spaces. So probably the most prominent example of this is Grothendieck's function sheaf correspondence. So giving certain sheaves, so when you have certain sheaves, you can produce functions, and Grothendieck advocated the philosophy that we should understand important functions as being the functions associated to certain sheaves. And we see this right throughout representation theory. And this, for example, is what underlies the geometric Langlands correspondence, that certain automorphic forms should be the traces of Frobenius, should arise as traces of Frobenius. And we also see this in much more mundane examples, but still extremely beautiful, for example, in Lustig's theory of character sheaves. And so this suggests the question of kind of, is there a Fourier transform for derived categories? And let me just say briefly that most functions don't support a Fourier transform. So somehow the Fourier transform on R comes from the fact that R is a group. And therefore we expect, and you can only do harmonic analysis in very symmetric situations, for example, for functions on spheres or things like this. And therefore we expect these tools to exist only for very symmetric objects. So categories of sheaves on very symmetric objects. And we kind of hope, so in analogy with the situation for the classical Fourier transform, so we think about a delta function as being something like a skyscraper or a simple object, and a fundamental frequency as being something like a vector bundle or a projective object. So we would think that kind of skyscraper should go to vector bundle, and so skyscraper is another word for a simple object. Projective object. Under Fourier transform. And we also expect that that it's rather special situations that support such a Fourier transform or such a equivalence. And just a beautiful example, which is not really doesn't really fit the this talk, but it's so nice, it's a pity not to mention it. And it's also I understand this is basically an algebraic geometry seminar, so that fits. So if A and A dual are dual abelian varieties, then we have the two projections, and we have the Poincaré bundle. The Poincaré bundle. So this Poincaré bundle is the bundle whose fiber over a point in A is the corresponding line bundle on A check. And we have the Fourier-Mukai transform, which is defined to be P1 lower star, P2 upper star of blah tensored with the Poincaré bundle. And this gives an equivalence from coherent sheaves on A check to coherent sheaves on A, which has exactly the properties that we're after up here. So a skyscrapers are exchanged with degree 0 line bundles up to shift. So, sorry, beautiful example.
Sorry, am I allowed to ask stupid questions?
Yes.
Great. So
who's this, by the way?
Oh, it's Jen. I'm a grad student at Harvard. So
okay.
so as someone who has absolutely no understanding of analysis, whenever I say the word Fourier transform, I think of Pontryagin duality. So, so what exactly do, like when you say, I understand this sort of analogy is pretty vague, but when you say you want to get some kind of categorical notion of such a thing, I mean, what is sort of, which direction is sort of going? So maybe what do you mean by Fourier transform in this context?
I mean, what I'm essentially looking at is, so the first thing is that it should be an extremely non-trivial autoequivalence of, not autoequivalence, but there should be some, it should be some very interesting equivalence of derived categories. So that's the first kind of thing that I would like. And the second thing is that it should have this kind of property of making things apparent on one side that are obscure on the other.
So it's a little bit sort of like Pontryagin duality.
Yes. Yes. And I would say that Pontryagin duality and the Fourier transform are kind of indistinguishable.
I see.
To some
Thanks.
extent. Yeah. Please ask questions, by the way. Yeah.
I also have a related question.
So
when you say Fourier transform on R, did you mean the classical one, the usual one?
Yes.
But it doesn't take the delta function to that thing.
Doesn't it takes it to a fundamental frequency, no? Just takes it to a
so
e to the.
You mean the integration with of fx with e to the power of 2 pi ix zeta some x.
Yes.
But that takes delta function to 0, doesn't it? Because yeah.
No, I thought it takes. Doesn't it just take doesn't it take dA to?
I mean, I think you didn't mean the real delta function. You mean some.
Oh yeah, probably. Yeah, no, sorry. I don't mean a real delta function. I just mean a function that takes the value 1 at A.
No, not 1. So it's the limit. So you take some approximation to something like take the value infinite in a certain point. So
no. I think we are integrating this over a distribution rather than a function.
No, there's some procedure that you can make this precise. You take some function some nice function that has limit like infinity on a certain point and 0 otherwise, and if we take limit, I think there's a terminology for that thing, but I can't remember the name. And for that thing, you will get the fundamental frequency.
Yeah,
anyway.
so I think that there's, yeah, so also I think it's correct what, I'm not sure who said it, but one can make this precise using distributions. Also, one should emphasize that, like, you know, both of these sides, for example, a fundamental frequency is not an L2 function, this sine wave is not an L2 function. But that illustrates something else, which is that often when we're in a derived category and we're looking for these objects, we need to be clever in terms of passing to some completion or something. So the fact that the fundamental frequency is not an L2 function is kind of also interesting in this story.
Yes, so yeah, I just want to say that. So it's not just the usual Fourier transform. You need to yeah. Anyway,
with some source.
Yeah. Thanks.
Okay. So yeah, as I said, this is an 8 o'clock talk, an 8 p.m. talk. So meta-mathematical problem. So basically what I want to explain now is that there are a whole host of equivalences like this that have this property of kind of being highly non-trivial derived equivalences that exchange, for example, simple and projective objects. And these are called Koszul dualities. And if you see the definition, so some people talk about, for example, Koszul rings, and there's some mysterious derived equivalence. What I want to explain is that a very efficient way of viewing all of this is via DG Morita theory. And so I just want to explain briefly what DG Morita theory is. And the mathematical problem is, imagine that I have some class of objects, so some objects, and I can ask this problem of kind of what can I build with, with this class of objects. So a simple example might be if I'm allowed to kind of take disks and their boundaries, and I'm allowed to start gluing, then I get CW complexes. And the glue is homotopy classes of maps. And this is why people care so much about homotopy groups of spheres, because these are the glue of algebraic topology. And similarly, I could take, for example, simplices on the left-hand side, and then I'll get all simplicial complexes and perhaps simplicial sets and things like that. Another example might be like Z mod PZ inside finite groups. So this is my class of objects, or I might take just the group Z mod PZ inside finite groups. And then over here, I get all P groups. And this is totally kind of, the glue is very, very difficult. Yeah, we have no idea how many P groups there are, basically. Another example might be, I might take some class of objects inside an abelian category, some objects. An abelian category. And now what is the glue here? So I can look at the kind of objects generated by A, and here the glue is kind of X's. And it's an interesting exercise to think about. If you start with some, for example, simple objects in an abelian category, can you predict ahead of time what the X will be? Once you start, like initially, you can calculate an X1 and you can build some objects, and now you want to know what are the new objects you can build with these, and you decide rather quickly that it's very difficult to see a priori from the beginning what's going to occur later on. And so although this question is kind of orders of magnitude easier than these questions, this question is still not really not particularly easy. But there's one case where it is very nice, which is when, let's say P is projective. And then we look at objects with a presentation. So P is, this is kind of P presented object. So this is, so object sitting here, then it's an easy exercise to see that if you hom from P, then this gives an equivalence with right and P modules. Or so finitely presented right NP modules. Okay. So this is an example where from the very beginning, we can completely describe what we'll get when we try to build all objects. Okay. And this is what people call, this is Morita theory. Okay. So Morita theory emerged when asking the question, which rings can have equivalent abelian categories of modules? And essentially this observation about projectives is the thing that allows you to solve this problem. So now what we're actually interested in is the case of a triangulated category. So that's exact case 4. So imagine that we have M in T, a triangulated category. So, and we want to understand the smallest triangulated category containing M. So kind of step 1 would be, we look at everything that we can generate from M as a cone. So we take a direct sum of some copies of M, and we consider some map to, this is I in I, J in J, and we consider some map, and then we have the cone. And now note that F is determined so F is some element in hom from here to hom from here, and I can write that in terms of the X algebra of M, which is just the direct sum of hom from M shifted by I, or I in Z. Okay. So the moral here is that if we're just interested in objects up to isomorphism that we can get in one step, so if we're only allowed to do one step of building, then this is determined by the X algebra. But so we might kind of hope is that M is determined by this X algebra. But the problem is basically the non-functoriality of cones. So when I write C here, this is an isomorphism class, but this is not functorially determined by F. And so now when I want to know how C is built out of, oh, sorry, that should be an M here. Now, if I want to do step 2 of this process, I run into trouble. I run into the non-functoriality of cones. And just to give you an example that this is really not, that this is problem of a fundamental nature rather than just we haven't been clever enough is the following example that I discovered last night whilst trying to think what to talk about today, is that if n is bigger than or equal to 2, we can consider lambda to be kx mod x to the n. And k is the simple lambda n module. And now it's a straightforward calculation to calculate the extra algebra of k. So we just write down a projective resolution and take do the usual procedure. And so we get k x if n equals 2, and k x eta modulo eta squared if n is bigger than 2. So this is of degree 1, this is of degree 2, and degree 1. So these two X algebras are isomorphic as vector spaces, but not as algebras. So notice that in each case, this simple guy generates the derived category of the bounded derived category of lambda n modules. And these are not equivalent for n not equal to n. I mean, yeah, so yeah. I can't really look into the audience and say, is this clear what I mean? I mean that dB of lambda n mod is not equivalent to dB of lambda n prime mod. When n is not equal to n. Okay, so there's no possible way that that this X algebra is enough. So, what's the moral? We need something more than the X algebra. And the source is given by the theory of DG algebras. Okay. Does anyone want to ask a question?
Yes.
So this can NM so thank you. Can NM be infinite? So you're asking, so is this kind of, I guess you kind of can also ask, like, what about the derived category of nilpotent modules over Kx?
I asked this question actually like 10 minutes ago, and at this point you were writing about, you wrote some equivalence, and I guess for this equivalence to be true, I guess it's, yeah, here. FP means finally represented?
Yes.
Then I'm still all right. Okay.
Okay.
Sure.
Are there any other questions? Sorry, I probably won't be able to continually look at the chat. So if there's a question, just in the chat, someone yell at me and say there's a question in the chat.
So I think.
Sorry. When you say two derived categories are different, do you mean they're different as a triangulated category, or different as in what sense?
I definitely, I mean, when I wrote that, I meant as triangulated categories.
So not with T structure or whatever.
Exactly.
Okay.
There's no derived equivalence between these two. And I don't know, probably someone can tell me a better way of seeing this, but one way that I convinced myself last night of is to look at the corresponding stable categories and see that these have different numbers of indecomposable objects. You know, it's never particularly, well, for me, with my limited technology, it's never particularly easy to see that two derived categories are different when their K-theory is the same.
Sorry, but the higher algebraic K-theories are different.
Okay.
Sorry, yeah.
Yeah, that's the technology that I do not possess.
Okay. Anyway, but yeah. If you look at, I mean, so something easy to compute is their topological cyclic homology. The ends appear in the TC groups. Okay, that's it.
Fantastic. Maybe afterwards you can explain what the higher K theory of these categories are. That would be great.
Perhaps.
Okay. Sorry, there was one more question, no?
Oh yeah, I tried to ask a question, but I think I understood. So yeah, thank you.
So ask it anyway in case someone else didn't understand.
Oh, I was trying to understand how this example illustrated this problem. But I guess what you are saying is that for n greater than 2, these algebras are isomorphic.
Exactly.
But the derived categories are different.
So they can't possibly be determined by these X algebras.
Well, that's mega spooky. Thank you.
Something spooky going on. But THC doesn't depend on the derived category. You need an enhancement to define it. Correct. But I guess all of these, I'm thinking about these as being, in this talk, I never actually mean a triangulated category. I mean a triangulated category with some kind of natural enhancement that's been handed to us, because they always arise with enhancement.
But if you have a algebra and you have a self-ext from trivial model to trivial model itself considered as infinity algebra, it's easy to reconstruct the algebra itself.
Can you repeat that, please?
I'll write it in the chat.
Okay. So, DG algebras and modules. So we have the notion of a DG algebra. Is a graded algebra plus a differential such that we have the Leibniz rule d of AB is d of AB plus minus 1 to the degree of A d of B. Okay, and as usual, the signs here are determined by the rule that kind of whenever you have to slide a d past something, you pick up a sign corresponding to the degree of that element. So here I don't have to slide d past anything. Here I have to slide it past A, and A has degree. And so just examples are any graded algebra with d equals 0. So this is kind of the case which we'll call later formal. And B, so this is a very important example. So imagine that I have a chain complex let's say in an additive category. Then I can form a curly end where curly end, I should call this J. J of C is just the product over Hom from Cj to Cj plus I. So over here, what we're looking at is Cj plus I, Cj plus I plus 1. And we're looking at maps, just any maps. Okay, so this is usually enormous. And this has an algebra structure given by composition. So algebra via composition. And a differential given by df. If I want to know the element in degree k, then this is d of f to the k. So this is, let's say that this is of degree I. Minus 1 for the I, f to the k plus 1 of d. So this differential, for example, on things in degree 0, it measures whether you're a chain homomorphism or not. And then we have the notion of a right DG module. So this is a graded right A module plus a differential from M to M shifted by 1, such that we have again the Leibniz rule, dA dot M is dA dot M M dot A. It's a right module. The Leibniz rule. And again, in the example, of course, if we have a graded algebra with, if we have a formal case, so the differential is 0, then any graded module is a DG module over this graded algebra. The kind of analog of B is if we have another complex, let's call it E, then curly Hom from C to M is a right C DG module. More generally, what's actually going on here is that chain complexes in this additive category is a so-called DG category. So Hom spaces with this definition of Homs between any complex, I can make this into a so-called DG category. And then I'm just looking at a tiny little residue of this DG category. Namely, I'm looking at the endomorphisms of a single complex, which is DG algebra, or the Homs from one complex to another, which is a DG module. Okay, and this is a kind of DG version of what we did before with the Morita theorem. So Hom from P is a right P module. Now we have the following beautiful diagram. Okay, thank you for the comment, Grigory. I understood what you're saying now. So the following beautiful diagram really helps me on an almost daily basis. DG So if we have a DG algebra, we can look at DG, so A is a DG algebra. Now we can do the same procedure. So if we think about the passage from chain complexes to homotopy category to derived category, we can do the same thing with DG modules. We just have to remember that there's some extra arrows going between degrees, but it works in the same way. So we have DG C of A. So this is chain complexes. So this is just the abelian category of DG modules. Now I'm worried it might not be abelian. Anyway, this is just a category of DG modules. And as with the case of chain complexes, we can look at DGKA, so homotopy category. And now we can localize quasi-isomorphisms. To form the derived category. Okay. Now, I want to assume that we have some abelian category A. And so here we can do the same thing. We can look at chain complexes in A. We can look at the homotopy category of A. And we can look at the derived category of A. And again, we have the quotient and localization functors. And now let's say I have a complex inside here. So this bit of the story is the bit that's really useful for me. So as I just explained, we have a curly Hom functor. So now we set A to be curly end of our complex. And so we can look at Hom, curly Hom from C And now it's easy to check that this descends. So check that this descends. So null homotopic maps descend to 0. And so we get this functor. Now, I want to make an assumption. So I can still consider C inside here. So I want to understand C here. And the assumption is that C is end acyclic. So what does this mean? This is the, so probably capital N. So this means that HOM in the homotopy category of A between C and its shifts is the same thing as the homomorphisms in the derived category of A. So e.g. C bounded above complex of projectives or are bounded below complex of injectives. But there's also other examples. For example, if you, for example, the theory of tilting provides end acyclic complexes also. So for example, if you have for example, a tilting bundle or something like that, that will also give you an end acyclic. So by a simple devisage argument, which I often, so there's a functor here, and if we look at HOMs from C to C, C to a shift of C up here or down here, we get the same answer. And now you can use long exact sequences and building up C to see that the full triangulated subcategory generated by C down here and here agree. And similarly, you can see that if we look at the kind of free DG module of rank 1, namely A, this is always satisfies the analog of end acyclicity. And so A inside here, this is what people call a K projective DG module. I should have said it before, but these are both triangulated. And the other beautiful thing in this story is that if I look at HOMs from C to C over here, from C to C shifted by M on the left-hand side, what I get is the mth xths of C with itself. And if I look at HOM from A to A over here, A shifted by M, I get exactly the mth cohomology of A, which is exactly what computes the xths of C with itself. And so again, a devisage, so what's giving us this is this. We get an equivalence across here. And so the kind of moral all algebraic triangulated categories are described by DG algebras. Sorry, I should say by DG module categories. And so at the moment, I'm phrasing this whole talk in the language of DG algebras, but there's this beautiful language of DG categories, which is more flexible. And then you can make this moral into a theorem. So inside any DG category, if I look at any class of objects and look at the full triangulated subcategory they generate, this is always equivalent to a category of modules over a DG algebra. This is kind of DG Morita theory. So this big diagram is basically the bones of DG Morita theory. Okay. So I guess I have half an hour left and the new rules of the seminar might start soon.
They start now.
What are the new rules? What are the new rules? You start drinking immediately?
Yeah, more or less.
Oh my God.
Every time anybody coughs, for example, or talks about finite characteristic.
Interesting. And I don't have to drink because it's 11 a.m.
Coffee.
Coffee. So now I'll just briefly touch on formality. And so are there any questions so far? Okay, so formality. So if we have A to A prime, a morphism of DG algebras, then this is a quasi-isomorphism if the cohomology of F induces an isomorphism of algebras. And this note leads via the normal roofs, etc., to the notion of quasi-isomorphic. i.e. A is quasi-isomorphic to A prime if A and A prime can be linked by a chain of quasi-isomorphisms where the arrows don't necessarily always go in the same direction. And we have the following theorem, which is that if A and A prime are quasi-isomorphic, then their derived category of DG modules are quasi-isomorphic, are equivalent via an equivalence that sends A to A prime. So often in my world, we're not so concerned about the ambient DG category, but we really care about the perfect category generated by this. And so this also allows us to conclude that these perfect categories are equivalent. And I'll just remark that somehow in nature, I back up here, in any realistic example, this complex won't be so small, and then this end will be absolutely enormous. And so what we want to do is kind of chuck away the unnecessary parts of our DG algebra in order to get something manageable. And if we can do this to the largest possible extent, that's what we call formal. So A is formal. A is quasi-isomorphic to its cohomology with differential 0. And many people have spent many, many hours of their lives trying to prove that DG algebras are formal. Okay. And just back to our example,
actually, in the previous theorem, you need quasi-equivalence instead of equivalence. I mean, DG models over A are only quasi-equivalent to DG models over A prime. Because, for example, endomorphism from A in the category of A models is A. It's not the same set as. I mean, you have several notions of equivalences of DG categories, and here you need quasi-equivalence, not equivalence on the norms.
Okay. You're saying this should be a quasi-equivalence of this should be quasi-equivalence here.
Yeah.
Okay. So in our example from earlier, if we take P to be the project, so remember our example from earlier had lambda n to be kx mod x to the n. And so we take some P, a projective resolution, and in this particular case, one can see with some difficulty. So, I'll explain a little bit in a second. So we can consider this DG algebra, which is controlling. So what we would like to understand is the full subcategory generated by K inside dB lambda mod, lambda n modules. And this is, this is everything. And this is formal if and only if n equals 2. So we saw that in the other cases we get isomorphic X algebras. So note that the cohomology of n of P is just the X algebra. Okay. So somehow hidden in this DG algebra is the kind of source that allows us to recover the derived category. Okay, so I was going to I can either do this example in detail, which based on the question so far might be a little bit of a basic example, so maybe I won't do that. Maybe I'll just explain the application to modules over the exterior and symmetric algebra and coherent sheaves on Pn. And then I will and then I'll just say about 3 words on the connection to Koszul algebras, and then we'll be done. So the origins of Koszul duality. So I don't want to, so I want to take V a vector space. Finite dimensional over K, which due to the rules just introduced is definitely of characteristic 0, but that's totally unnecessary. And I want to look at the exterior algebra on V, to look at the derived category of graded modules over the exterior algebra on V graded modules, where V is in degree -1. Now, if we apply DG Morita theory inside this, we can look at the full subcategory generated by K. And now I want to consider the triangulated category plus, I also want to allow shifts in the grading. And what we get from kind of what we might call DGG Morita theory. So by that I mean differential graded graded, because now we have two gradings. We have the homological grading and we have the grading of vector spaces. Is that this is equivalent to, so to dB of S of V dual now, so how do we compute the X algebra of K? So we write down a projective resolution as a lambda V module. But if we do this via the Koszul resolution, we can see that in fact the algebra that we get is formal. So this is one of these rare instances where we prove formality by just demonstrating a DG subalgebra, which is formal on the nodes. We can just lift the X guys to actual classes they compose as we want. So in my experience, there's two ways that you show formality. Either you just roll up your sleeves and do it, and this happens very rarely, or there's some big theorem, for example, using weights and purity and things like that, that allows you to deduce formality. And in this particular case, you can actually do both, but I won't go into that. Plus formality. And now, now this thing has degree one. So if we picture what a complex inside here looks like, it's a whole lot of vector spaces. And it has an action of S in this direction. And then it's got a differential in this direction. And now what we can do is this following very amusing trick is just to shear this so that we sum along these pieces. And now what we have is literally a complex of graded S modules. So this is the shearing trick. And this becomes dBs. And I'm missing this should be differential graded dgs.
Excuse me?
Yeah.
V lives in the degree 2-1, right? Or is it 1-1?
I thought it was 1-1, but I have to admit I didn't do this calculation this morning.
I mean, if V is one-dimensional, then on the left you have the category of k of x modulo x square modules where fx lives in the degree -1. So you want to compute self-x of k over k of x modulo x square, and I guess it's k of u where u lives in degree 2. Right? I can probably write it down. If it's
okay, maybe it's not so. I mean, yeah.
Yeah.
We're in an epsilon neighborhood of the truth.
Right.
Maybe 2-1.
Can I ask what you wrote on the right hand side? Some shear or something?
Yeah. So sorry. This is what. So I claim that if you just kind of look combinatorially, what an object in here looks like, what a DG module looks like, it's a bigraded vector space. So this is meant to be my picture of what it looks like. So it's a bigraded vector space in which you have kind of horizontal differentials. And then it's also a DG module. It's also got this DG module structure. So it's also got an algebra action, but the algebra action is diagonal, like this. So like in the one-dimensional case, where this is just a polynomial ring in one variable, then this has a differential going in this direction, plus an operator going in this direction. And now there's a simple way of just what I want to do is straighten this. So if you see traditional Koszul duality, you will notice that there's some extremely bizarre relation between shift of grading on the left and shift of grading on the right. So this is a triangulated equivalence, so it can't mess with the triangulated structure, but it can mess with the shift of grading functor, and it does. And so this is what I kind of mean by re-shearing. So
I see. Thanks.
And you'll notice that shift of grading here, like if I do what's a good color for shift of grading? So here might be my shift of grading functor. So that's shift of grading. Over here, that corresponds to something like this. So it corresponds to -1, 1. And if you see something like this, it's a sure sign that Koszul duality is at play.
Can I ask a question which is more appropriate to an 8 p.m. talk? Sorry.
Sure.
So what is the exact relationship between the words Koszul duality and formality that you're trying to get at this picture that I'm somehow like almost.
So can I answer this this in a few minutes, because this was going to be my final point.
Amazing. Yes, thank you.
Okay, so the end of the day, so there's some kind of little tricky, so DGG Morita theory naturally lands me over here, but now I can kind of use the two gradings to regrade and and we get an equivalence between this thing and this thing. And now, what was the kind of problems of linear algebra? So remember that dB SG mod modulo the full subcategory generated by the trivial module. This is equivalent to dB co Pn. This is Sayre's description. So if I divide this category out by the full subcategory, the Verdier quotient generated by the full subcategory generated by the trivial module, I get coherent sheaves on projective space. And what happens over here? So the trivial module goes to the free module over here. So this becomes equivalent to dB lambda graded modules divided out by, so this is what you might call the stable category. Okay. And so the paper that kind of began Koszul duality is called Coherent Sheaves on Pn and Problems of Linear Algebra by Williamson, Bernstein, Gelfand. And Williamson has a paper at exactly the same time establishing the same theorem, and I think they were talking to each other, so maybe you can view this as a kind of 4-author paper. So here's your coherent sheaves on projective space, and here's your problems of linear algebra. And I guess when you first see this, you think, coherent sheaves on Pn, that's really hard. Modules over an exterior algebra, that looks like a finite dimensional algebra, and that's easy. And then you realize that just both sides are hard. So I'll just finish by saying what does this have to do with Koszul duality? Koszul duality as we now kind of know it. So let me just go back one slide and emphasize up here that K over here goes to S over here, and lambda over here goes to K over here. So this does indeed look like it's exchanging simple and projective modules. So this is the kind of Koszul duality. So we have a positively graded ring. Semi-simple. And now this is Koszul. If xi of A0 with itself is concentrated in degree I. Sorry, I didn't prepare this slide, so it's maybe minus I. Now, what one can use is, one can use the lean trick So I have 4 minutes, so I'll just say what the trick is. So I believe that this was first noticed in Deline's papers on weights, is that any bi-graded DG algebra with cohomology concentrated in degrees on the diagonal II is formal. Okay, so if we have a bi-graded DG algebra whose cohomology is concentrated on one diagonal, so we have lots of different bits of our algebra, but the only things that contribute to cohomology live along this diagonal. And this is a really lovely exercise. So there's a two-step quasi-isomorphism between A and its cohomology. And then the Deligne trick implies that this end of A0 is formal. And so we again get an equivalence between dB of A mod. So this is equivalent to DGG Yeah, so it's not entirely 100% correct what I'm writing down at the moment. So, but if you followed it from here, you can fill in the details. And again, we have this shear equivalence to dB of X A0 graded modules. Okay. And this equivalence sends simples to projectives. So the simples are precisely the quotients of A0, and these get mapped across to the projective modules over the X algebra. Okay, so and that's the connection with the what people understand as when they say Koszul algebra in a classical sense. Okay, so thank you very much.
Thank you.
Amazing.
Thank you. Yeah, that's very nice. Thank you.
Yes.
Are there any questions for the speaker?
Yes, I do have one. So it seems like this is a very powerful trick, this interplay between simples and projectives. Can you give an example of where, something like this is applied?
I guess in some sense it's kind of my whole subject.
I see.
So in representation theory, there's this kind of interplay between, for example, in category O, over a complex semi-simple Lie algebra, there's these initially very mysterious relations between simple objects in category O and projective objects, and all of this is explained by Koszul duality.
Right.
And it's interesting. So one thing that's maybe rather interesting in this story is that somehow on the Grothendieck group, Koszul duality looks very easy. So in our world, it's often, for example, just sending Q to minus, so Q to something like minus Q inverse or something like that. For example, you have various inversion formulas that they almost look like they're trivial, but then when you try to lift them up to a categorical level, they tend to be these very deep Koszul-like equivalences. So, yeah.
Well, what Q inverse, sorry?
So up here, when I said you have this relationship between shift of grading and homological shift. So over this side, this -1 would probably correspond to something like a shift of weight, which is a Q. And over the other side, it corresponds to, in this particular case, this would correspond to minus Q.
I see.
And so replacing Q by minus Q looks like a pretty innocuous operation.
Right. But on the level of the DG categories, it's like something very interesting, I guess.
Yes.
I don't. Has anyone? I mean, okay. I guess as you guess by now, I do like algebraic K theory, and I wonder if there's been any interaction between, how this kind of like non-trivial shift can be detected on the higher K groups. If people have looked at this. I mean, I don't know any rep theory myself. So.
Yes, I don't know. But maybe someone else has an example where, because I think that this analogy with the Fourier transform suggests that there should be many instances where something on the other side of Koszul duality is patently clear, whereas it's not on the original side.
Right.
And I don't honestly know so many examples of this.
Anyway, thank you.
I might have like probably this follow-up example on this abelian varieties. So when we're sending skyscraper sheaves to the corresponding sheaves, I think it would there are no morphisms between different skyscrapers, at least like morphisms in degree 0. And so it's kind of this delta function explanation of why there are no morphisms between different stable objects.
Another beautiful instance of this is Atiyah's classification of vector bundles on elliptic curves.
Yes.
Becomes totally trivial when you go to the other side of Fourier-Mukai.
Very cool.
So I think I have a question about the Koszul duality, because I mean, for example, from the view of like DG algebra geometry, I mean, we can always regard A as some kind of affine DG scheme. So I think I wonder that whether we can generalize the Koszul duality for example, for other DG schemes.
So this has been worked out to some extent. So a really beautiful example of this is like a simple example of a DG scheme is just the kind of self-intersection of the 0 section of a vector bundle inside the total space.
Yeah.
And this was used by Merkovich and Risch to explain certain formulas in the modular representation theory of Lie algebras. So some kind of local Koszul duality, but it's a very simple instance of it. But That's an example where those ideas have been used.
I see. But is there any way like we're gluing the local causal duality to some kind of global thing?
So this is a global causal duality. So it's locally not particularly interesting. It's just this example that I gave here, but it turns out to have global implications that are interesting in their work.
Are there any other questions?
Yeah, can I ask a question? So in the business of Fourier transform, when you construct a Fourier transform, you usually use some kernel. Can you say a few words? Can you see the kernel here? Or?
That's a really good question. Yeah, so I think so we know several instances of causal duality now, and essentially none of them are explainable by a kernel as far as I can make out. And I think it's a really fascinating question to understand geometrically. So for example, in certain categories of perverse sheaves, there's some remarkable autoequivalence, and we have no geometric understanding of why this autoequivalence is there. We describe both categories in terms of algebra, and then we apply causal duality on the level of algebra. I think it's a really excellent question to explain this via a kernel, but I have no idea how to do so.
But in this simple case, for example, in BGG duality, should I think about Koszul complex as a kernel of Fourier transform or no?
I think the answer is yes. You're totally allowed to do that.
I think that I think that in this case, so there are two exceptional collections on Pn, two dual exceptional collections on Pn, and they are related by this causal complex kernel, resolution of the diagonal, and endomorphisms. Self X of one exceptional collection is lambda, and of the other is S.
Mm-hmm.
I see.
Yeah, but
so that's an example where it's given by a kernel. Great.
Yeah, but I'm not sure if I can like make it more formal for Kostya.
I think that you can treat the universal twisting chain between algebra and its bar construction as something of this kind.
Yeah, I think that if we use this language, we can write down like in the DG modules language, but I think more the question is in these instances where we're getting some interesting equivalences of, for example, coherent sheaves or perverse sheaves, can we explain this in the geometric setting via kernel? And that I think is much more rare.
Yes, thank you. Thank you.
Other questions? Okay, if there are no other questions, let's thank the speaker again.
And did anybody notice that there's actually somebody up here in the air?
Isn't it a glitch?
Oh.
No, it's actually a person.
Yeah.
Oh, crap.
I wanted to see if anybody notices. Okay.
Okay, yeah. Thanks a bunch for the talk. I mean, like, I might not be able to sleep tonight because I can't decide if I'm too excited or too scared by the talk, but yeah, especially, but that's non-formality example.
Samantha, it's because you didn't drink enough.
Yeah. I should finish my my cider.
Okay. So see, we have a visitor, so I should go and drink a cup of tea with them. But I'll see you guys later.
Thank you.
Yeah. Thanks again.
Yeah.